Hello, everyone. Welcome to my lecture, Advanced Exploration Seismology. My name is Yanghua Wang. I'm a professor of geophysics. My major in the exploration seismology. The objectives of this lecture mainly consist of 3 points. Understanding steps leading to the stack and migrated seismic section. They are standard products. The stack section is a seismic imaging of subsurface structure, because when we record the seismic data in the time sequence, so seismic data is a function of time. That means in your seismic stack section, the vertical axis usually is time rather the depth. Therefore, the stack section is not exactly the subsurface imaging. Then we need to actual step, which is migration. We move the structure to the true position in terms of depth. So this is the first objective. The second objective is you should be able to carry out a basic seismic processing sequences. Basically, through the practice, you will be able to understand the concepts better, much better in terms of the understanding of the physics behind. And any mathematical formulas involved will be quite simple. So you need, if you understand the physics, right? So those equations in this lecture, only a few equations, they actually derived based on the straightforward physics. You do not need to memorize all the equations or the formulas I present here. Maybe only 1 or 2 formulas, which is straightforward to memorize, but others you will be able to write down your own equations if you understand physics. So practicals are important for everyone to understand the concept involved. Right, the third objective, you appreciate the limitation of seismic data in the context of assumption made in the processing. You do not assume after data processing your result will be 100% reliable in terms of geological structure, geological feature. That's the key. And also, in terms of each step of processing, you understand the assumptions made, and then you can understand the assumption made, and then you can somehow to relieve the assumptions by some degree, and then you can see the difference in terms of the final imaging, I mean the stack section or migrate section. So if you eventually become a geologist, you should be able to identify some assumptions behind, so that you can convince yourself if any geological feature appeared on the seismic section, they are really true there. They are really true structure. So there are 3 objectives. For the reference, one of a good reference is this one called Seismic Data Analysis. That's quite a heavy book, 2 volumes. You can easily get a copy from Imperial library. Other slightly light references, it's not as heavy as the previous one. They are all involved in the exploration seismology, or sometimes called reflection seismology. The first two books are authored by Sheriff. Typically, the second one is for introduction to the exploration seismology. The third one is authored by one of our professors in this department. The second author, Professor Michael Washington. And actually, the structure of my lecture here quite similar to the structure of that book. The title of the book is called Seismic Data Processing. So you can see we have limited resources to access to the field for the practice, but we focus on the seismic data processing. If you understand the seismic processing, understand the requirement for the seismic processing and the imaging, you will understand the basic parameters or basic requirement for in the field acquisition. This lecture will be delivered in totally 9 days. The first 8 days, I dedicate this to 8 sessions, and the last one, the day 9, will be a review session. Most likely one session for 1 day, but for the first session, I need more than 1 day because we try to introduce some basic math or basic physics for the course. Students from a different year, third year, fourth year, may or may not take some fundamental courses, but I here they try to cover some fundamentals. So that means everyone can go forward together. Day 1, the Seismic method, just the introduction. In this first lecture, I will introduce 3 parts. First, the basics of Seismic method. Second, as I said, we need to review some background knowledges. And the third one, where I just illustrate how to do the seismic acquisition, includes the acquisition geometry, acquisition equipment, and how to do the quality control. So basics of seismic method. Seismic industry or seismic science starts from this big event. That's one of historical events, thinking of the Titanic in 1912, just 110 years ago. But by that time, Titanic is a giant ship, and then nobody expect to have such disaster occurred. Right. We know what happened because of foggy day and the midnight, the giant ship hit the iceberg, right? Okay. Because of that, Wang meant here, he applied for a patent. This gentleman is a Canadian inventor. He's one stage he worked with Edison, and he's the first person to broadcast his voice on the radio. And he invented the loudspeak. The patent I mentioned actually is for acoustic iceberg detect. And in the same pattern, he also mentioned that this same principle can be applied to detecting the subsurface anomaly, which is the principle of seismic exploration. The pattern looks like this. This US pattern applied on the September 18th, 1917. There are two figures. The top one, in the four corners, there are 4 sensors, and if one sensor receives the signal directly from top left to the bottom right, if you send out a signal and receive by this one, because you know the water velocity, so basically you know the distance between here to here, right? Between here and here. But if you receive a second arrival, which is travel longer, and because here the iceberg here have a refraction, and the travel longer, that means time delay. Based on the time delay between this pass and the straight line pass, you can find out the distance of the iceberg aside, right? And also you have, if the signal transmits through the berg and received by another receiver, you can work out the thickness, or so basically the width of this iceberg, right? And for this one, you have a sensor from here to here, the travel distance, but also have a reflection back to here. So you also can find the distance, this one from here, right? This is an iceberg detector. Uses sonic signals. Right, in the same pattern, he also said, okay, same geometry can be applied to the subsurface. If we have the source here, and the receiver here, and the receiver here, right? Or source here, receiver here. So that's the receiver can receive the sonic from here, goes through this anomaly, and then received by this one, and also you can receive here or here. So that means based on this acquired travel time, you can detect the anomaly here, right? If there's no anomaly, basically you do not have reflection back. You see, that's the important thing here. So that's exactly the principle for seismic acquisition or exploration seismology. In the modern days, this geometry we call the cross-hole. If source in one borehole, receiver in another borehole, receivers are in another borehole, it's called cross-hole seismology. If a source and the receivers are in the same borehole, and wave travel in the neighborhood of a borehole, this wave logs we are quite familiar with. And if a source and the receivers are moved to the near surface, not exactly on the surface, near surface, right? You have a wave travel from a source down to the subsurface, and the reflector from the anomaly back to the near surface. This reflection seismology. So this is the principle of reflection seismology. So the acquisition, if we have a source near the surface, and then we have a series of receivers on the surface. The receiver on the surface, in the industry, we often call it geophone, just like iPhone, right? Geophone, so geological phone. And instead of a single anomaly, small anomaly, but you have a contrast between this layer and the next layer. So this have a strong contrast, which is called a reflector. So your wave propagating from source down to the surface, down to the interface, and then come back to the surface. That's the geometry of reflection seismology. And the receivers here, you record the signal and then transmit to the recorder. And the plot this receive the data. You have a picture which is called a seismogram. That's the principle of seismic exploration. So what we actually measured in the surface. So we simply call that what we record, what we measured is called seismic wave field. Right. So physically, what is the seismic wave field? It is elastic wave motion on the surface, right? Or some of its variations. We will see later. And recorded in time and space. Space, I just said, your receivers spread out on the surface. Time means you record from a time 0 to certain time. So you record a series of samples. Usually, as I said, the receivers are at the surface or very close to the surface because the scaling of the Earth structure, we treat everything almost near the surface, on the surface. Right, we will see details in the section 3, just see how the depths of receivers affect the seismic record. The wave field most likely are just two quantities. One is called pressure, one is called particle velocity. Pressure is a scalar, basically measures the media, in this case most likely be the water or fluid, right? The compression and the explosion. So that's called pressure, which is scalar. But also, typically for length acquisition, we measure particle movement in the vertical direction, in horizontal direction. So it's a vector, and the vector contains multiple components. Wave field is about elastic wave motion and its variation. Sometimes you can even measure the particle acceleration. So particle velocity, and then you do one more order of derivative, you get a particle acceleration, right? Velocity and acceleration, that's differ in one order of derivative. If you do an integral over the time, you will come back to the particle velocity. So that's basically there are two quantities. This one you can easily transfer back by integration, transfer back to the particle velocity. That's the wave field. And when we analyze the wave field, we should easy to identify the type of motion. The type of motion is related to the wave mode. let's review that. So the first primary wave mode is called P wave. P stands for primary. Is compressional wave. So the compressional wave means you have a pressure on the stress on the top, on the left, and then your particle move left to right and left to right, left to right. Okay, so any particle here, when they push the particle rightwards, and then this particle hits the neighbor particle, and the neighbor particle move forward. So this is the way. Travel direction of the wave is from left to the right, and the particle motion is also follows this direction. That's called compressional wave, the compression explosion. Another type of wave called secondary wave. S stands for secondary. It's a shear wave, or when the wave propagation along this direction, but the particle movement is perpendicular to the propagation direction. This is called the shear wave, right? Because the particle movement is perpendicular to the propagation direction, so at least there are two type of shear wave. One is vertically perpendicular to the propagation direction. Another one is horizontally perpendicular to the propagation direction. One thing here I should emphasize, this shear wave cannot occur in the fluid, right? Because in the fluid, in the water, the shear modular is 0. The similar to the previous two mode, but not exactly the same, is so-called surface wave. One of the type of surface wave, just like the P wave. However, magnitude of particle movement decayed from surface down to the Earth, right? So that means you have a strong motion in the near surface, and gradually the magnitude of motion gradually decayed. So this is called a Rayleigh wave. Another surface wave, just like the shear wave, so you have the particle movement perpendicular to the propagation direction, and the motion of particle movement is gradually reduced from the near surface down to the Earth. Right, this two type of shear wave in the earthquake seismology. These two waves actually reckoned as the most damaged wave, all right, in the near surface. Surface seismic wave is the focus point for the earthquake seismology, because this near surface movement caused huge damage to the human life. Now, in the exploration seismology, actually we treat the body waves, which is P wave and S wave, the body waves as a signal, because we try to investigate the deep part of the Earth rather the movement on the near surface, right? So different from the earthquake seismology. The body wave is basically the wave propagating inside of Earth, so-called body, right? Inside of a cube. media. And this gives us the information structure, information on the structure inside the Earth. The amplitudes actually decay inverse proportional to the distance traveled. To understand that, you can understand the energy conservation principle. So if we have a point source, right, with a small radius, the spherical shape with a small radius, and another spherical shape with a large radius, but the total energy on the surface are the same between those two. So the surface, this surface area is pi r squared, right? So that's the energy. The amplitude is a square root of that, so it's a 1 over r. That's its body wave energy. Mentioned here, well, we'll compare this to the surface wave later, right? And generally, in the exploration seismology, we use P waves. Sometimes, occasionally, use shear wave. We'll discuss later, right? In the exploration seismology, we treat the surface waves as noise, right? Because they travel along the near surface and they do not give us information on the structure inside Earth, right? However, this one is very difficult to separate from the signal because the amplitude decay is 1 over square root of the travel distance, right? So basically, after same travel distance, for example, 100 meter, 1 over square root of 100 is 1 over 10. So energy decayed by 10%, right? But in the body wave, in the previous slide, 1 over 100, which means after travel 100 meter, the amplitude decayed to 1%. This here's 10%, that one's 1%. So in this case, the signal is 10 times smaller than the noise, or noise is 10 times stronger than signal. So that means we do need to do the signal processing to try to remove the noise, to reveal the weak signal from the data, right? We reviewed the surface wave has 2 types. One is called Rayleigh waves, one's called a love wave. The first one is similar to the P wave. The second one is the particle motion similar to the shear wave. We said there are 2 quantities we often recorded for the waves. One is called the pressure, another is called the particle velocity. When the wave getting upwards from the subsurface to the surface, we call the U here, which is upgoing wave from a subsurface structure, come up to the near surface. And when this wave reach to the surface, because the surface is a strong reflector, strong interface between the air and the subsurface, either water or the soil, right? So because strong contrast between air and the Earth's surface, so the upgoing wave will reflect downwards from the surface downwards. So basically, on the surface, there are two components. One's upgoing, one's downgoing, right? And the total pressure will be the sum of the U and the D. For particle velocity, because the particle velocity is a vector, right? So you will have the vector U and D have a different direction. So the recorded particle velocity will be the difference between the two. And the units, you need a factor to get a unit right. It's usually proportional to the inverse impedance. Those are the two types of quantities we measure. One's P, one's V. The difference between the two, the pressure pressure is a scalar, but the particle velocity is a vector. So that's the difference. Because one is a vector, one's pressure, let's see what we can acquire in the land environment or in the marine environment. Right. Let's see. At the surface, the downgoing wave from say this black line here is surface, right? You have an upgoing wave reach the surface and then going down. So the downgoing wave is related to the upgoing wave by a refraction coefficient, right? So D equal to R multiplied by the refraction, the upgoing wave multiplied by the refraction coefficient. In the marine environment, the R is absolute, roughly -1, right? Because both the air and the water are homogeneous media, and almost 100% of energy reflected back. So this is a very good assumption for the marine environment. But for the land, because of the near surface structure, the different material on the near surface, so that will be more complicated. Right, so that means in the marine environment, because R is -1, so downgoing wave plus upgoing wave, that's almost 0. So that means we cannot measure pressure on the surface. We do need put the pressure measurement below the surface, right? However, for the land seismic, it's difficult to put the receiver down to the near surface. So most likely we need to record the particle velocities. If we can put the receivers below the surface, we can measure either pressure or particle velocity below the surface. Let's just show you one of the fundamental principles of seismology. Assume we have a layered subsurface structure. In this case, we have 6 layers. Each layer has a different physical properties. Because the difference in the properties, in the physical property, so they appear as the contrast here appears as a reflector. This reflector has a different coefficient, reflection coefficient presented here. So velocity difference, basically. So this layer and this layer velocity, first one is 2,000 meters per second, second one is 3,000 meters per second. So difference is small. So that means you have a 90% of energy reflected back to the surface, right? The second one, 300 to 350, you have a reflection coefficient 0.6, and so on and so forth, okay? So this is in depth, and each layer physical property represented by different velocities, and the difference between two layers is quantitatively given by reflection coefficient. Ideally, we record from the seismology should be something like this. We recording receivers on the surface. We're recording in time, so you should have a series in time, the units in second, and this the reflectivity series, right? That's the ideal situation. This is what the ultimate target we try to do, right? In fact, we cannot record the spark look like this, sharp spark, but in fact, each of these actually presented by something called a signature, a source function here. For the red one here, the source function multiplied by this reflection coefficient, you end up the red here. And there's this sky blue here, you have here, and basically the reflection coefficient magnitude is multiplied to the wavelet, and also the priority here. For example, this one, negative priority, so you have negative priority. So each of these reflectivities, actually in the seismogram is represented by a wavelet. Sum of them together becomes a single trace, right? You know where this from, but practically you don't know. You only have a seismic trace with same color, right? So your seismic processing and interpretation, you should be able to extract this reflective series based on this time sequence, right? You can see very complicated seismogram. So that means your analysis will lead to multiple solutions, right? That is the problem. The principle is called superposition, which means your seismogram actually is the sum of all this individual waveform. So you sum it together, the superposition. Mathematically, it is called convolution. Superposition mathematically is a convolution. We are talking about convolution in that second session in detail. Now, as we said, the seismogram seems quite complicated, and because we don't know what exactly the subsurface structure is, right? So we should treat the seismic trace as a black box, right? So, however, we can assume reasonably that these two properties, one is a time invariant, one is a linear. Time invariant means the subsurface structure does not change dramatically within time. For example, we acquired the data last week, and today we acquire the second time at the same place, same geometry. These two data sets can be simply summed up, make a single data set, right? So it's time invariant. And then the summation is linear. So the linear is a fundamental assumption for the superposition. When in the previous slides we showed all the wavelets summed together may have a different weight based on the reflectivity, but they are linear assumptions. So there's two fundamental principles we explored in the seismic data analysis. And every reflection, as we showed in previous cartoon, right, it's a copy of an instant disturbance I called seismic wavelet. We call seismic wavelet, right? Ideally, we should record the reflectivities, right? However, we couldn't. What we actually acquired from the field is the wavelet. So the effective wavelet is equivalent to filtering the reflectivities, filtering the sparks. And the result, based on the superposition, the result can be calculated use convolution. The convolution means the seismic wavelet is convolved with a series of subsurface reflectivities. Right, here, this is the first session of today's lecture. Thank you. We'll see you in the second session.